All right, so the point I want to make today is that when we looked at our lab, okay, the two reactions that we made, we had reaction 1, reaction 2, and we used Hess law using the reactions. We took the delta H's of these reactions to get the overall, which was the third. When we had to flip the second, change the side, add them together, I bet we got a delta H of this reaction, enthalpy, that approximated very closely to the delta H of the reaction that we got with heats of formation. I'm saying that this value is probably closer. And you're saying yes, correct? Across the board. If you did not do a heat of formation of the third reaction, if you did not use products minus reactants, look up the heats of formations of those and put them together like the homework, then we can't have a conversation. But for those that did, this should approximate closer than this value that came from Hess law manipulation of reactions to the what? The calculated delta H. And I'm telling you right now, these delta H's have error in them because of, like you said, loss of heat. Is there more loss of heat in one or the other? Well, there's more heat being exchanged, definitely. So my question is, these aren't definitely known. Okay? Now, what I did yesterday, and this is important, is we looked at a way to think about Hess law, whether it's manipulating reactions or using heats of formation. I call this the FAS zone, free atom zone. Now, when we have chemical reactions, let me give me the delta H of one reaction. A reaction 1, what was the delta H? The delta H was, so negative 61. Negative 61, okay. And that's, of course, kilojoules per mole. Now, in truth, okay, that has to be some distance. All the heats of formations of the products and reactants should come up to that value there. What was number 2? What'd you get for number 2? Someone just give me a number. I don't care if it's not the same person. Smaller, right? Negative. Okay, negative 5.3. Okay. Now, negative 5.3. Okay, so these are the two reactions. Now, when you manipulate them, okay, they eventually become some distance between them. Now, I know that we wound up adding them together, but the point I'm trying to make is, and again, is that where this is kind of a rough estimate based upon what? Based upon energy being lost to the environment. So is this one. So the individual values are. But when you compare them to each other, who cares what the actual value is here or here? When you, okay, based upon our limitation in this lab, the distance between the two, that's what we're after. That's going to be a heck of a lot accurate than what the actual values are. Okay, and that's what's so important about Hess's law. Now, let's go back to yesterday. Okay, yesterday we're talking about, very quickly, okay, talking about a free atom zone again. And we had a couple of things going on here. Rough yesterday, we talked about the fact that if I have NaCl, solid, and we had some value for the heat of formation of NaCl solid, okay, I don't even care what the number is, and then we took the individual heats of formation. Now, again, I can't say enough, heats of formation are from your atoms. They're not bonded, they're elemental states, okay? And if you go from the elemental states of atoms, free atoms, if you don't understand what that FAS means, free atom zone, these are the highest energy of atoms, okay? Now, from those atoms, we make a product. Now, we make another product, okay? Well, if I find the heat of formation of sodium ions, it was some number. It wasn't as negative as this, okay? And then when we found the heat of formation of chlorine ions, I'm going to kind of piggyback that. So when I added the heat of formation of sodium ions, and chloride ions together, when we added the products, okay, we got some value for the chloride ions and the sodium ions, which are aqueous. And we saw yesterday the difference to that position is a positive delta H. Now it was small, okay? It was approximately a positive, was it 3.8 or something we got, or 4? About 4. And because it's positive, we saw that, hey, in my reaction, my ionization reaction, sodium chloride becomes, okay, Na plus aqueous plus Cl negative aqueous in water. This is an ionization reaction. And now we have a delta H. Remember, delta H is going to have a bunch of different names to describe the state function of the energy change in constant pressure. We call this, I didn't mention this yesterday, but now we need to give it a new name so you recognize it. This change of H is change of H of dissolution. Dissolution means the energy change in a solution. Okay? In this case, it's going to be approximately positive 4 kilojoules per mole. Now, what does that mean? That means when I drop sodium chloride, that's my chemical, in water, that chemical, when it dissolves, takes in that much energy. And that's going to do what to the solution? Make it colder or warmer. It's going to make it colder. It's going to take energy. If you don't see it, draw an energy diagram. Here's water. Sprinkle in sodium chloride. This is going to take energy from its environment. And therefore, the solution gets colder. Cold packs are made this way. What cold packs normally are is a bag. And in a bag is a bag of water. And then there's salt, type of salt. You pop the inner bag of water, and you mix it, you shake it. And if the heat of dissolution, which is basically the change in energy, enthalpy, is positive, that's an ice pack. If you use a salt that has a heat of dissolution that's negative, that'll be a hot pack. I don't know if you guys have ever seen those, okay? And I used to have a couple out. All right? Now, in table I, now we don't have this table, of course, on an AP, but this is tying into your Regents curriculum. Okay, we've got this table I again. And table I showed combustion reactions yesterday, but on the bottom, it shows ionization reactions. So I look here, and I'm just going to put this over all my drawings here. We can see, and let's make it minus here. I'll take it darker, or less white, I guess. I'm not doing anything. Okay, so let's do dark. I don't know what I'm doing. Good enough. Okay. So if you look at table H in all of its glory, all right, in fact, why am I even bothering with this? Let's just go here. We're going to see that, we'll see, Sky Drive, Public, Share Drive, reference tables, stay with me please. Okay, so let's go to table I, I's have it, and we get bigger, up close and personal, and what we have is ionization reactions, okay? And so some of these salts, when they dissolve, have a positive heat of solution, or heat of dissolution. So what they just call it, dissolving, solution, dissolution. That's where they get that from. But in any case, these guys all make the water what? Colder, because it's what kind of process, endo or exo? Endo. So where would I write the heat in my reaction? I know this is basic, and we haven't been through this, but I make sure we're on the same page here. Where do I write that energy? I write the energy in my reaction right here. And because heat of dissolution is what? Per 1 mole, I can write approximately 4 kilojoules here. Because I have how many moles here? 1. So I put the heat. Sometimes you'll see the heat written. So energy here means positive. Okay, so they have 3.88. All right, so does that make any sense? Bottom line is yesterday we were able to predict what the delta H was of this solution by using heats of formation. Powerful way. Don't have to do the calorimetry anymore. And that's what your homework was about. But the idea is that we're using the product's heat of formation minus the reactants. Biggest mistake people make. And why? Because that will give me the positive value, meaning going up or going down. And if we do another thing that we've saw in previous courses, is we write a potential energy diagram for this process. What would that look like? Well, if I'm going up, I'm starting low, I'm going higher, and sometimes you'll see this process for chemical reactions. Here's my what? Reactants, here's my products. And the difference of where I start and where I finish is the positive 4 in this case, or the delta H. That's all, no big deal. Okay? If something is endothermic, if a chemical is endothermic, the environment gets cold. Chemical is exothermic, the environment, the surroundings gets warmer. Now, if you look at your reference tables, okay, let's go to your reference tables. Your table, heat of fusion is there. Okay, let's go back to reality here. Let's go to your reference table. I don't want to do that. So I go to your reference table, all right, and that is going to be here, maybe. Here we go. Thermo AP tables. Let's make that bit up close and personal. Now, as I said yesterday, hard to find. These are my delta H's of formation. Now, very important, party people. These little zeros mean that we're at certain conditions. 1 atmosphere of pressure and 25 degrees Celsius. Those are standard thermodynamic quantities. So part of this lab that we did, even though we're basing it upon heats of formations, our lab isn't at 25 degrees, 298, Kelvin. So it may not be at 1 atmosphere of pressure. Okay, so what I want to say to you is that look at these heats of formation. Forget these right now. Most of them are what? Why are most of them negative? When chemicals as free atoms bond, don't they get more stable? So therefore what happens is energy must be released. Okay? Now of course in the problem I'm showing you here, water dissolving, it's already starting in this position. So we're moving to a new position, but the reason why Hess laws works is because all of these chemicals are referenced from this point. So the difference of them, as long as we have a state function starting and stopping, we can connect all of them. All right, now notice something else. Sometimes I've got zeros here. Why do I have zeros? Because those are these elements in the zone. If I have the elemental states, they will be 0. Okay, so if you have a diatom, look at graphite. Okay, notice diamond is positive. In order to go from graphite to diamond, there has to be a what? Look at graphite, 0. Look at diamond. Delta H of F is positive. What does that mean? It takes a heck of a lot of energy to make this into this because we need tremendous amount of pressure. Okay? But for most of them, they're negative. You should know the ones that are zeros are the elemental states, especially your diatomics. Okay? All right. Good enough. Now, something else you need to understand here. If I'm talking about dissolution, okay, whether a reaction gives off energy or absorbs energy when it dissolves, solution, dissolving, dissolution, we have to understand the same understanding. It must mean if this is positive and this is endothermic, the ions in water in this case are more stable or less stable than the solid. If it's endothermic, less stable. Somehow these ions are not as stable. And you need to explain why. What kind of attractive forces exist in dissolution, dissolving of a chemical? These sodium ions are going to be attracted by the what? the negative part of water, and it's going to completely surround them. The chloride ions are going to be completely surrounded by the what? The positive part of water, which is the H. Now the question is, if it's less stable as a solution, okay, it must mean that water isn't really attracting them that well. Now we know what's really stable in crystal field splitting, being highly positive and really small, water makes a complex. In fact, some of the water's electrons goes into the d orbitals to make what people think are sometimes covalent bonds. So why isn't sodium plus and Cl, why aren't they stable? We started this process in September, and now we're going full circle. Why aren't these stable? They're too darn what? Yeah, the Coulombic attractions are too weak because they're too what? Big, and their charge is what? Too small. So water has a tough time getting around them to dissolve. They have a +1, they have a -1, but they're big ions. These ions are always spectators. Okay, so water is a tough time. Now, if I give you another salt, okay, that when it dissolves, okay, is exothermic. Look at this one. Look at sodium hydroxide. When it hits dissolution, heat of dissolution is negative. So it's exothermic. Temperature of the solution goes what? Up. Because when this dissolved, energy's what? Released into the solution. Now why? Well, we still got sodium plus. What's the difference here? The heat of formation of the hydroxide ion must be what? Really, really negative. Must be really stable for the hydroxide in water. Okay? And why? Hydroxide is small. Okay? And water can actually react with it too a little bit. So this being so small and negative, okay, drives this. What else? Look at these guys. What's the difference? Lithium plus. Sodium plus. You can just see that water has a tough time surrounding. What lithium plus? What's the difference? Yeah, N equals 2. It's smaller. Water can wrap itself around that, contract it more, stabilize it, have a stronger attractive force. So therefore, it's negative. And by the way, that's why we use lithium-ion batteries. Okay, solutions of lithiums can be more stable. So when we look at heats of formation and we look at heats of dissolution, you must be able to explain why dissolving of a salt, the dissolution of a salt, is exothermic and endothermic. If it's exothermic, you know that the ions, the products, are more stable than the reactant, because water can have a stronger, we call this molecule ion attraction. It attracts it more. Okay? If we have an endothermic salt like this one, water has a tough time attracting it. It does attract it, but the attractions aren't as strong. This is not a more stable kind of scenario. All right? And that's why it takes energy to create that. And it's all about the ions, the size, Coulomb's law. All right? Any case, when things dissolve, it's important you realize a couple things are going to happen. Water has H bonding with itself. This salt here has an ionic attraction. Somehow water has to be able to overcome its own attractive force of its H bonding to what? Work in those ions. So if water doesn't attract ions as well, okay, it's not going to be it won't be as stable as water itself. And those are called essentially ideal solutions. All right, moving forward. All right, I feel like without doing this, I should show you clearly that, where is my Lager probe? Oh, here it is. So, booyah. I mean, I feel it's kind of silly, but hey, I'm tall and silly. So let's get a temperature reading up here. Maybe. Plug this guy in. Do I have a temperature? Yep, 22. Okay. I'm going to spin this baby to its heart's desire. Okay. Now in truth, spinning should increase the temperature, but not significantly enough. Okay? Christmas and July. I'm having a good time today. Really am. Hold on. This is supposed to go fast and easy, but it's not. As I'm told. There we go. I can do this. All right. Now, so I got water at about 22. And I'm going to drop sodium chloride in. Imagine that. Woo, what a demo. Okay? But sodium chloride, table salt, okay, being NaCl, is going to have a positive heat of dissolution. So because water cannot become as stable as it likely, you can create an unstable scenario, so it's going to grab energy, okay, all right, from the environment so that water can do its best to get around these big ions. So throw some salt in here, and our temperature should be dropping. And it is. It certainly isn't dropping a lot. And why isn't it dropping a lot? Well, number one, what is the heat of dissolution? Positive 0.4, okay? So it's not a huge. Now, if this was positive 20 or 40, what would the temperature do? It would drop a lot more. Remember, it's always what? Heat per mole of the substance. Okay, lame demo, I know, but I felt like I needed to do that. Okay, now getting back to our tables. Let's go back to our tablature. All right, let's go back to this guy right here. Where am I? Here. Anyone see something? Let's look at aluminum oxide. Aluminum oxide. Aluminum oxide has a heat of formation of negative 1675.7. Compare that to aluminum chloride. Okay? It's pretty darn high. So what does that mean? When aluminum oxide is made from its elements. And what would be that reaction, by the way? What would be that reaction? That's a skill you must have. What's my product? Yep, aluminum oxide. Okay, it's made of its elements. What's the elements? Aluminum. And because oxygen is diatomic, it's O2. So we need what? Well, if I make this nicey nice, 2 here, I need 4 of these, and I would need what? To get 6 oxygen, I need 3 here. But this is per what? That little circle means 1 atmosphere of pressure, 25 degrees Celsius, 298 Kelvin, and these guys are the value per 1 mole. So I can't write it that way. So cut it in half. Cut it in half. Cut it in half. That's the reaction. Okay, per 1 mole. Tremendous amount of energy. Why? Because the products are more stable or less stable? More stable. You're looking at an energy diagram, potential energy diagram, where we're going down a lot. So the difference of where we start and where we finish is a bigger negative. Why? Aluminum is what charge? Plus oxygen is negative. What do you think the lattice energy between a -2 and a +3 is? Remember lattice energy? That's the delta H of the energy to break the crystal apart. It's going to take a lot of energy to go in the reverse. If I want to go in the reverse and break this up, if this is negative, where's my number? The energy is going to be right here. Plus 1676, I'll round off kilojoules. Right? My heat goes on the product side. Okay? If I want to break this crystal up of aluminum chloride, aluminum oxide, I need tremendous amount of energy. Okay? So this is called the thermite reaction. If you've got aluminum, okay, or at least in this case, if you got aluminum and you want to make aluminum oxide, if you're making this product here, all right, this is what we call part of a thermite reaction. All right? So we're going to let's do that thermite reaction. Okay, now, the product here is aluminum oxide. So I'm going to show you what this looks like. I have 2 rusted spheres. Okay? And so these are iron oxide. All right? And what I'm going to do is I'm going to smash them against aluminum. Okay? Now, where I'm getting the oxygen from, and let me show you the reaction, okay, is I'm going to make the final product to be aluminum oxide. All right? So let me show you the reaction. This is the heat of formation of aluminum oxide, but I'm going to show you how it's tied to what we call the thermite reaction. Okay, the reason why it's so gosh darn exothermic is because we're making aluminum oxide. So, here is the thermite reaction. By the way, the thermite reaction is a really important one because the only bomb ever dropped on the continental United States was one by the Japanese. Okay? At the end of World War II, to scare us into thinking there was a possibility you could get to the coast of United States, what they did is they basically put like very old planes on like barges. They didn't have they were losing the war effort, of course, and to go that far, they could never have the fuel of an aircraft carrier. So they had I think biplanes or prop planes. Obviously, at that time of the war, they only had propeller planes, and they had them on barges. I think they had like 20 that went out to try to get to the west coast. Supposedly because of storms, only one made it. Plane took off to barge, and they lit a thermite reaction, just dropped it. Okay, it wound up burning in the middle of the road and didn't do anything. Okay, but it was a bomb dropped by a foreign. And so here's what we have here. I have iron oxide. Okay, now iron oxide is rust. Okay, 2 and 3. And I'm going to smash it with aluminum. Okay, and what's going to happen, all right, is I'm going to make aluminum oxide. And this is the cool part. Okay, pure iron. What kind of reaction is this? Single replacement, which is an example of a redox reaction. Here's a 0. Here's a 0. This guy's -2. Oxygen's still -2. If this is -2, what's the charge of all the oxygens? Negative. This is +6. There's 2 of them. Each iron is plus. Good. -6, +6 overall. Each one is +3. Look at the half reactions. Aluminum 0 becomes what? Aluminum +3. Where do the electrons go? Everything's interrelated. Right, I need 3 of them to make each side 0. Okay, you got what? Iron +3 needs 3 electrons to become iron 0. So party people, what's so amazing about this demonstration is that there is so much heat released because we are making what? Aluminum oxide. Oh, plus iron though. What's the heat of formation of iron? So the amount of heat we're releasing is due to this guy. He's 0, and the iron oxide somewhere. So the tremendous amount of heat given off here is really due to the low heat of what? Formation of aluminum oxide. So, this is the micro version. And I want to show you the macro version. I don't want to do it because thermite's dangerous. If I start a thermite reaction, a big one, I can burn a hole, okay, through the floor into the next classroom, okay? I almost burned a hole through my lab table up there. Okay, so thermite are very hot and very dangerous. So what's really cool about thermite reaction is that because so much energy is released in making this a stable aluminum oxide particle, the heat released is enough to actually melt the iron that's produced. Okay, so I'm going to slam aluminum oxide spheres together. So aluminum is going to hit with my activation energy. I should get some good sparks. The sparks that you see are actually going to be liquid iron that's glowing for a little bit. So I have my old clothes on today because inevitably I get holes. Okay, aluminum is getting oxidized. Iron, remember how reactive aluminum is? Aluminum is a pretty reactive metal. Okay, here we go. So I should get some sparks here. So it's kind of cool to do it in a dark room, but hey, it's all. So. I don't know if you're seeing those sparks. That was a good one.
I've seen this on like Man vs. Wild.
Okay. Now, if you can see that where I had those sparks, the aluminum's gone. The aluminum is now a dust of aluminum oxide. Just like yesterday, the heat formation of my very exothermic well. There's a little white, that's a little white dot, it's not that crazy, but there's a little white, I don't know if you can see that, there's a little white dot in there, that's a sodium chloride, okay? Now, let me show you a little bigger scale. Because, hey, I'm told. Then, so what I have here is iron oxide. So I have rust mixed with aluminum. It needs a lot of energy to start because I have iron oxide in a what? Crystalline pattern. So my striking gave it, so I have to use a special fire starter. So I'm using a fire starter, and there's the reaction. Now it's hard to see, but it went so violently. What you see dripping is molten iron. So, molten iron. So the iron in the iron oxide became reduced, got gained electrons, and the heat, because of the stability of the iron oxide, okay, melted the iron. I don't do this inside anymore because I just don't trust myself. Okay? All right. Now, one last question. It's based upon, okay, table, and I have a worksheet for you to do for homework. It's not a big deal. Tonight's load is low. I hope you have that. You look at this one last thing. In the middle of table I, they have these reactions. Notice they're all synthesis reactions. Notice they don't have this one. Look at that value. But that's per what? So if I wanted to compare in Regents land, I have to divide by what? Who's got stronger bonds? Aluminum oxide? NO. Aluminum oxide does a what? Greater negative. Okay, there is a worksheet. Just pick this up on the way out. It's the only homework you have. Yes.
Oh my God, Siobhan. Shut up.
So just turn that off.
Yeah. Bye, Rose.